Hi, good day. Today we are going to talk about integral domain. This section aims to define integral domain and find the zero divisors of a set, and thus the proportion of the integral domain for different kinds of sets. Now, let's discuss zero divisors. If A circle dot B and A is not equal to 0 and B is not equal to 0, then we call A and B as zero divisors. For example, in Z4 as in the table, and please take note that Z4 here is closed under multiplication modulo. So now let us try to fill in the composition table with its values. So 1 circle dot 1 is equal to 1, 1 circle dot 2 is equal to 2, 1 circle dot 3 is equal to 3, 2 circle dot 1 is equal to 2, 2 circle dot 2 is equal to 0, 2 circle dot 3 is equal to 2, 3 circle dot 1 is equal to 3, 3 circle dot 2 is equal to 2, 3 circle dot 3 is equal to 1. Then 2 is 0 divisor of Z4. Now let us find the zero divisor of C6, Z12, C3, and Z5. For Z6, we have two zero divisors. We have 2 and 3, since under close multiplication modulo 6, 2 times 3 is equal to 0. In Z12, take note that Z12 here is closed under multiplication modulo 12. So in Z12, we have four zero divisors, namely 2, 3, 4, and 6. How about Z3? Z3 contains no zero divisor because we find no integers a and b such that a times b is equal to 0 under close multiplication modulo 3. The product happens only when a and b are both 0. Now let's proceed with Z5. Again, take note that C5 here is closed under multiplication modulo 5. So now let's fill in our composition table by its values. So we have 1 circle dot 1 is equal to 1, 1 circle dot 2 is equal to 2, 1 circle dot 3 is equal to 3, 1 circle dot 4 is equal to 4. 2 circle dot 1 is equal to 2, 2 circle dot 2 is equal to 4, 2 circle dot 3 is equal to 1, 2 circle dot 4 is equal to 3, 3 circle dot 1 is equal to 3, 3 circle dot 2 is equal to 1, 3 circle dot 3 is equal to 4, 3 circle dot 4 is equal to 2, 4 circle dot 1 is equal to 4, 4 circle dot 2 is equal to 3, 4 circle dot 3 is equal to 2, 4 circle dot 4 is equal to 1. Thus, based on the table, Z sub 5 contains no zero divisor as it is indicated in the table. So theorem 6.71 says that Z sub P, or the ring that contains the integer modulo P, for which P is a prime number, contains no zero divisor if P is prime. Now let us define integral domain. So integral domain is a commutative ring without zero divisor and with unity. What do we mean by unity? Unity is the identity for the second operation. So example 6.7.2 show that Z3 is a commutative ring. So we have the property closure property. Z sub P, or the ring of integers modulo P, where P is a prime number, is closed based on the table. In other words, for any two elements, A, B, element of an integer, we have a circle plus P, element of Z. This means that upon performing the operation addition modulo n, to any elements of ZP, we cannot find any other element in the table except the elements of Z sub P. Another reason for Z sub P to be closed under addition is that the elements of Z sub P are integers and Z, the set of integers itself, is closed under the ordinary addition. Associative. The operator addition modulo n is associative since the elements of C sub p are integers, and the ordinary addition is associative under Z. Identity. The identity addition modulo n is 0. In other words, for any element in Z sub p, we have A circled plus 0 equals 0, circled plus A equals A. Inverse. Element 1. 1 circled plus 2 equals 2, plus 1 is congruent to 0. We have 2 as the inverse of 1. Element 2. 2 circled plus 1 equals 1, plus 2 is congruent to 0. Then we have 1 as the inverse of 2. Commutative. The operator addition modulo n is commutative based on the table. So this means that the elements are symmetric with respect to the main diagonal. This symmetry implies commutativity under the operation addition modulo n. Closure. ZP is closed with respect to multiplication modulo n. The closure property under multiplication modulo n can also be based on the mere fact that the elements of Z sub p are integers and Z is closed under multiplication. This means that for any elements AP, elements of Z sub p, then we have A circle dot P, elements of Z sub p. Associative. The elements of Z sub p are integers, and the ordinary multiplication is associative under Z. Thus, circle dot is associative under Z sub p, or multiplication modulo n is associative under Z sub. Distributive. The distributive property is implied by the mere fact that it holds under the set of integers. Thus, for any elements A, B, and C, elements of Z sub P, then we have this equation. Thus, Z sub P addition modulo n multiplication modulo n is a ring. Commutative. The operator multiplication modulo n is commutative since the elements are symmetric based on the main diagonal. Thus, Z sub P is a commutative. Zero divisors. Z sub p contains no zero divisor. This means that A times B equals 0 will only happen if A or B is 0. But we cannot find other integers A and B in C sub p satisfying the property. A circle dot P equals 0 and A is not equal to 0 and B is not equal to 0. Thus, Z sub P contains no zero divisor. Unity. The unity of Z sub P is 1. Thus, Z sub 3 is an integral domain. And that's all for today. Thank you for watching, everyone. Keep safe.